Hello everyone, let us continue our discussion. So this week our topic is buckling and this is the last week and we are in third lecture. So we have already defined Euler buckling load. Today let us solve some problem. Now let us consider a hollow circular cross section. So this is our example 1, and for this problem we have a column. As you can see here, the column length L is 5 meter and the ends are hinged. So we have one hinge here and another hinge there. Young's modulus E for this column is 2.1 into 10 to the power 5 Newton per millimeter square. Now the diameter, outer diameter, capital D, is 35 millimeter. And the wall thickness T is 5 millimeter. Our task is to find the P critical for this column. So from the given dimension we can find out inner diameter small d, and small d is 35 minus 2 into 5 because the thickness is 5 millimeter. So the inner diameter is 25 millimeter. Now once we know the inner diameter and outer diameter, we can find out I for this cross section, and the I for this hollow circular cross section is pi by 64 times d to the power 4 minus small d. So what we have is pi by 64 into 0.035 square minus 0.025 square. So if we evaluate, we get 5.45 into 10 to the power minus 8 meter to the power 4. Now, for a hinge boundary conditions, the Euler critical load P critical is pi square EI divided by L effective square, and L effective in our case is capital L, and that is 5 meter. Therefore we have pi square into E, which is 2.1 into 10 to the power 5 Newton per millimeter square. So it is 10 to the power 11 Newton per meter square, multiplied by I, which is 5.45 into 10 to the power minus 8, divided by L effective, which is 5 square. So if we solve this, we get 4.5 into 10 to the power 3 Newton. Therefore, P critical for this problem is 4.5 kilonewton. So you can see how from the dimension we can estimate the critical load for the column. Okay, so let us take a second problem. Problem 2 is the same one. So we consider the same geometry, but both ends are fixed. For the problem 1, find the P critical for this case. Now, if both ends are fixed, we know P critical is 4 times pi square EI by L square. Recall, L effective in this case is L by 2. So it means we have 4 times pi square EI by L square. So this part is what we have already evaluated for the hinge case. So the capacity for the fixed boundary condition is 4 times the critical value for the hinge case. So it is 4 times 4.5. So this is equal to 18 kilonewton. Now you can see, if you compare this value with the previous one, you can see just by changing the boundary condition how much the critical load is affected. So earlier we had a hinge boundary condition, and from that point, if we change the boundary condition to fix, the critical load increases by 4 times. Okay. So now let us consider a different problem. So this is example 3. Now in this example, we have a weightless beam which is actually supported by 2 columns at the end. So this is the arrangement. Now for the column, the one on the left, we have fixed support at the bottom, while the same for the one on the right is hinge. Now both this column has hinge at the top, and this beam is massless. Now let us apply a load P over this beam. Our task is to estimate this P, given that Young's modulus E is again 2.1 into 10 to the power 5 Newton per millimeter square. The length of the column L is 3 meter, and the cross section, which is rectangular, and it is 3 inch by 3 inch, so roughly 75 millimeter by 75. So our task is to find the magnitude and location of P corresponding to fast critical buckling load. That means the moment we apply the load P, which is actually transferred to the column, and you can see these are the column loads. The reaction at this hinge point is upward. So if the load here, reaction upward is say P1, and here the reaction upward is P2, then obviously a compressive load will be acting over the column, right? So let us mark the compressive load only. Now obviously for this problem, our task is to first find out, we have two different columns, one here and second one is here, and because the beam is massless, no load from the beam, the weight of the beam will come to the column. Let this distance be x. So we'll find out the distance x and also the magnitude P. So let us first consider column 1, and for that the moment of inertia I is equal to 1 by 12 into B and D, they are same, so 0.075 BD cube, so we can write 0.075 to the power 4. Now if you evaluate this, we have 2.64 into 10 to the power minus 6 meter to the power 4. So for column 1, we have P critical, say 1 is equal to twice pi square EI divided by L square. So we have 2 times pi square times 2.1 into 10 to the power 5 Newton per millimeter square. So that will be 10 to the power 11 Newton per meter square times we have 2.64 into 10 to the power minus 6 divided by L square, so that is 3 square. Now if you evaluate this, it is 12.16 into 10 to the power 5 Newton. So that means 1216 kilonewton. Now for column 2, P critical 2 is equal to pi square EI divided by L square. That means this is equal to P critical 1 divided by 2. So if you evaluate that, you get 608 kilonewton. Now we can solve the first question. P, that is the total load, is P critical 1 plus P critical 2. So if you sum these two values, 1216 plus 608, we get the total load 1824 kilonewton. Now, the distance between the column, so this distance, say 1.5 meter. So now we can find out x applying moment equilibrium. So if we consider, say, this point is A and this point is B, we can now take the moment about A. So if we do that, we have, let us write here. So we have P times X, that is, we consider this load here, times X is the lever arm. So that is the moment caused by the force P about the point A is equal to P2 times the lever arm, which is 1.5. So that means X is equal to P2 is 608 times 1.5 divided by 1824. And if you solve this, it is 0.5 meter. So the distance, this distance is equal to 0.5 meter. So from the left end, if we put the load of 1824 at a distance of 0.5 meter, then that will create two forces P1 and P2 acting on the column corresponding to the first critical load, and both of them, both the column will together simultaneously reach their first critical load, right? Okay, so that solves the third problem. Let us consider the last problem of today's lecture. So, example 4. Now, in this problem, again, we have a beam and we also have a column. So, this is the arrangement. And for this arrangement, again, we have hinge at this point and the beam has hinge at the end. The column is also having hinge at the bottom. Now, this distance is 0.5 meter and the other side we have 1.5 meter. There is a load, point load acting downward. So this is P. Now this length of this column L is equal to 3 meter. Young's modulus E is again 2.1 into 10 to the power 5 Newton per millimeter square. Cross-sectional area, cross-section is circular with diameter D is equal to 75 millimeter. Find the value of P. So, let us mark A, B is the beam and C is the point where the column is connected. So, CD is the column. Now, the point C is going to have a load, and for the column, this is the first critical load, because the moment this load acting at the point C reaches first critical load, the column is going to fail. So from this arrangement, we have to find out what is the value of P. So let us first find out I. So it's a circular cross section. So we have pi by 64 times d to the power 4. D is 75. So the value is, if we convert it into meter, so we have 1.55 into 10 to the power minus 6 meter to the power 4. Okay. Now P critical we can evaluate, and that is pi square Pi by L effective, which is again L because we have hinge boundary condition. So L square. So now we get pi square into 2.1 into 10 to the power 5 Newton per millimeter square. So it will be 10 to the power 11. And then we have 1.55 into 10 to the power minus 6 divided by L is 3 meters, so 3 square. Now if you evaluate the safe critical and first critical load, it is 356.95 kilonewton. So now, given the arrangement, you can see the beam is having a length of 2 meters. So if we consider the moment about B and satisfy the equilibrium, so what we get is P times 2, that is the lever arm, is equal to 356.95 times the lever arm is 0.5. So from this we can find out what is P. P is equal to 89.24 kilonewton. Therefore, we get the safe value of P, which will initiate the buckling in the column. So if we apply a factor of safety, say 2, so we can find out safe load to avoid buckling, that is 89.24 divided by 2, and this is equal to 444.6 kilonewton. Okay, so you can see how we can use the concept of buckling and then solve these problems and find out the critical load, first critical load obviously, because the column is going to fail when the force, compressive force on the column reaches its first critical buckling load. And we can also design the safe load for different structural arrangement. As you can see here in this case, we have beam column arrangement, and using the factor of safety, we can find out the safe load that we can apply on the beam to avoid any failure, right? With that, let us close here. We'll continue on this topic in our next class. Thank you very much.